Alright, so let's do an example of the Gram-Schmidt algorithm in action. So suppose you're given a matrix. This is your input, right? Let's say 1, -2, 1, 2, -1, 2, 0, 3, -1. Alright, so this matrix has a column space, space of outputs, and the Gram-Schmidt algorithm is going to come up with the orthonormal basis, with an orthonormal basis for the column space. And you see, if we are going to get, for instance, three vectors in this orthonormal basis, this is going to show that A actually has column space all of our three, right? And therefore means that the null space is trivial and that these are linearly independent. So it's an alternative way actually to analyze this, instead of using the reduced rational form. Alright, so let's start out with these vectors. Is give them names, u1, u2, u3. And step 1 consists in simply taking u1 and normalizing it, right? So w1 should be u1 over the norm. Okay, so let's compute the norm of u1. That's the square root of, 1 squared plus -2 squared plus 1 squared. Okay, which is root 6. So w1 is 1 over root 6 u1. Or in other words, 1 over root 6, 1 -2, 1. Okay, and then w1 is the span of little w1. So this is the line spanned by this vector. Alright, so step 2. Now we want to take u2, right? We skip over to the next vector, and we want to project it onto w1. But we already have a nice orthonormal basis of w1, in this case just little w1. So the projection is actually fairly simple. It's just an outer product times u2. Or another way to, if you change the parentheses here, this is saying that you have to take u2 dot w1, w1. Alright, and let me use this form here for w1, because it actually in this case will simplify a little bit. So I have to take u1 root 6, u1 root 6. So the 2 root 6 actually come out and they give me just a sixth. And then all I have to do is u2 dot u1 and then give that to u1. So I just have to take the dot product here across. So 1 times 2, -1 times -2, and 1 times 2, so I get 6, right? So 6, and that cancel, so you just get u1. So that's nice. So the u2 actually just projects onto u1, and now I take the difference, right? I need to take u2 minus this projection, the orthogonal component, which in this case is u2 minus u1, and so that's going to be 2 -1 2 minus 1 -2 1, and what do we get? 2 minus 1, minus minus 2 minus 1, 2 minus 1. Alright. Sorry. This is there. Alright, so Great. And so finally, to define W2, W2 is the normalized orthogonal vector, so it's going to be U2 minus the projection over the norm of that. So in other words, I need to take the norm of this, which is root 3, and normalize it. Alright, so that's W2. Let's just check. It's always good to check that W1 and W2 are orthogonal. Let's just do a quick check here. So if I take the dot product of 1 over root 6, 1, negative 2, 1, with 1 over root 3, 1, 1, 1, the root 6 and the root 3 factor out. Really what matters here is 1 times 1, negative 2 times 1, and 1 times 1, so you get 0. Yeah. Alright, so that's good. We are on the right path. And now, let's do the last step, step 3. Okay, so what do we have to do here? We need to take the third vector, 0, 3, negative 1, and we need to project it onto W2. Oh, I didn't define W2. W2 is the span of W1 and W2. So how do you project onto a subspace like W2? Well, it's the sum of the outer product. So it's going to be W1, W1 transpose plus W2, W2 transpose applied to U3. This is the projection matrix P2 onto W2. Alright, but more, if we expand here and then do the usual trick, this is equivalent of saying that you take U3, dot it with W1, and assign that coordinate to W1, plus U3 dotted with W2, and assign this coordinate to W2. This is the equivalent thing. Okay, but this is a little bit more manageable. So we need to take U3, which is 0, 3, negative 1, dotted with W1, which is over here, and it's got a root 6 in front, and then assign it to W1. So the root 6 add up to a sixth. So we do that, and it simplifies like this. Now for this here, W2 has a root 3 over here and a root 3 over there, so that comes out as a third. And then 0, 3, negative 1 now has to be dotted with 1, 1, 1 and assigned to 1, 1, 1. Alright, we can do this. Okay, so 0 times 1, negative 6, negative 1, so negative 7, 6, 1, negative 2, 1, plus a third, 0, 3, minus 1, that's 2, 1, 1, 1. Alright, we need to do some algebra here. So negative 7, 6 plus 4, 6 is negative 3, 6, so that's negative a half. And then we have 7 thirds plus 2 thirds is 9 thirds, that's 3. And then the same again, so negative a half. Alright, so that's the projection of U3 onto W2. But remember, we need to take the orthogonal component of that, right? So what we've done here is we had U3 and then there was like a plane, this W2, and we've projected it down, and we found this projection, but now we want the difference here. We want this component over here. Alright, so let's do that. So what is U3 minus the projection of U3 onto W2? Alright, so U3 is 0, 3, negative 1. And the projection is negative a half, 3, negative a half. Alright, so minus minus, you get a half. 3 minus 3 is 0, minus 1, minus minus a half is minus a half. Let's take the half out. It's 1, 0, negative 1. Alright, so that's this vector here, but it's not normalized. Now a trick here, when you normalize a vector, constant factors don't really matter, right? So you just have to normalize that. So W3, which is U3 minus the projection of U3 onto W2 divided by its norm, that's just going to be 1 over root 2, 1, 0, negative 1. Alright, so we are done now. We've got W2 over here. We've got W1 over there, and then we got W3 over here. And you can check that this is an orthonormal basis.